We're going to continue kind of our topic of kinematics. Last lecture we went over some very fundamental concepts. Just do a quick review. We talked about two types of motion, right? We talked about constant velocity motion, right? Very simple, very straightforward. Your velocity is kept constant, right? So there's no acceleration. Acceleration is actually zero, and the governing equation for any constant velocity is v, or average v, is equal to displacement divided by time. That's it. That is your governing equation. There's no variability on that. And then we talk about a slightly more complicated case, which is constant acceleration, which means your velocity is actually changing, but it's changing at a constant rate, right? So, and we said a governing equation here is really average acceleration, right, is equal to change of velocity over time, and this is a constant, right? In other words, you have v final minus the v initial divided by t will give you the average acceleration. Keep in mind, I keep on saying the term average because BC, actually, at least physics B deals with mostly average velocity, average acceleration. When you get to C, we're going to talk about instant velocity, instantaneous acceleration. It will be a different topic, which we'll go over for those of you who are interested in C in a separate lecture. So, and when I said when we expand this, right, because we really want to work this displacement concept into this equation, so we basically integrate these two and got the next two equations. It says, well, the first one is displacement is equal to initial velocity times time plus 1/2 at squared. That's a very useful one in case you don't know the final velocity. You can work that, right? Or another one says v final squared is equal to v initial squared plus 2a delta s. That's another version. What's missing here is the concept time. So we did a couple of examples in the last lecture. It depends on what conditions are given, right? You can solve these problems according to the different equations that allows you to basically go ahead and tackle these. So this is really the foundation of kinematics, at least for AP physics, in the sense that this is as hard as it will get. You say, well, you know, this doesn't look too bad. It's not, right? Let's take a look at an application of this constant acceleration motion. It's very common. You get tested all the time, which I like to call free fall. What's a free fall? Well, here's free fall. You have something, you let it go, right? You let it go and it drops. That's free fall. What kind of motion is free fall? What causes free fall? Well, what causes free fall is what? Gravity, right? Gravity constantly pulls on the chalk, so unless I'm holding it, if I let it go, gravity is gravitate this towards the center of gravity, which is the floor in this case, and it will drop. Right? There's nothing else dictating the motion. So free fall, in an ideal case, a free fall motion is a constant acceleration motion. Okay? Except in this case, we know what the acceleration is, at least on the Earth. The acceleration on Earth is what we describe with a little g, gravitational acceleration, right? And it's 9.8 meters per second square on Earth. Okay? This acceleration changes when you go to a different planet because gravity is different, and then in subsequent topics we'll discover forces, we'll talk about planetary motions, and gravity will discover why this is different. But on Earth, it's a constant, at least close enough to the surface. It's 9.8 meters per second square if it's on Earth. On the Moon, slightly less. Okay? So free fall questions are great because there's a constant what? There's a constant number that we already know. We know the acceleration. So for all of these, we already know, right, what the A is. In this case, is G, right, 9.8. And one thing you got to watch out is that this always points downwards. So be careful with the sign because, again, we're talking about vectors, so signs are very important. The best way to illustrate this is show you guys how an example works. So let's take a look at this. I have, I'm at the cliff of a mountain, and that's ocean, right? I take a box and I drop it. Okay, simply drop it. I have basically a timer in my hand. It basically took me 3 seconds for me to see that the box hits the ground or the water underneath that, whatever it is, right? I'm going to ask you, how high is a cliff? Okay, how high is the cliff? So you look at this and say, well, there is a lot of things going on. Let's do what we normally do. We list what we know. What do we know? Well, when I tackle a problem that start to get it a little bit complicated, that it has more directions, I always define a direction, right? In this case, everything seems to go downward, so I'm going to define downward as positive, okay? Just out of habit. All right, one thing I know it takes 3 seconds for this box to drop from this to that, right? And I know I'm looking for the height, which is really what? The displacement of your box. Oh, that's great. I know one thing, and I need 3 other things, right? Now, if you're dropping this straight down, what is the only force that's acting on? It's gravity, right? That means the only acceleration this guy's experiencing, because I didn't throw it, I just let it go, right? The only force, the only acceleration that this guy's experiencing is gravitational acceleration, right? In this case, I do know A, which is positive 9.8 meters per second, because A or G is going this direction, right? Along the same direction as defined as positive. So everything's cool, except I just have 2 things. What else is true? Do we know something else that's implied in this problem that we didn't know before? Yes, we do. We know the initial velocity. What is my initial velocity? I didn't move it. I simply let it go. The instant I let it go, the velocity of the box, that instant, was what? 0 meters per second squared. Again, always watch out for these implied conditions, right? 0 meters per second. So, here we go. I know 3 things. I know the time, I know acceleration, I know initial velocity, I'm looking for displacement. You go back here and say, well, which one can I use? This one seems pretty solid, right? Let me put out an equation. Displacement is equal to initial velocity times time plus 1/2 at squared. Plug it in. Initial velocity is 0 times time is 3 plus 1/2. Just for demonstration purpose, I don't like to use 9.8. I just use 10 for acceleration, just to save a little bit of time. And then t is 3 squared. So displacement actually turns out to be 5 times 9, 45 meters. Amazing, huh? I give you one known, the time it takes for the box to drop from here to there, you find out how high the cliff is. Amazing, right? Think about it. From that, because there are 2 conditions that are implied that you should know as a good physics student, you should know that already, and combined with the one you know, plug into the equation, and you're done. Okay? Very, very straightforward. This is actually what they do if they want to measure the altitude of a cliff. They literally just drop something, right, and measure the time it takes for that to hit the ocean underneath, and it can measure the altitude of the cliff. So it's a pretty neat trick, right? Very interesting. So very simple example, but without the extensive understanding of physics, it could be difficult, right? And if you try to memorize a lot more equations, deal with free fall questions, don't. I'm telling you guys, that's all you need to know. Identify whether or not it's a constant velocity or constant acceleration. Well, it's a free fall, so it's constant acceleration. You know the acceleration. List out the knowns, list out the unknowns, find an expression, plug in, and you're done. Keep it simple, keep it straightforward. Okay? Let's kind of go along the same line. Let's take a look at a different scenario. All right. This one's a little bit more complicated. Instead of having the box just drop it, okay? I'm going to toss it up. I'm going to toss it up at 1 meters per second. All right, just, a little toss. But eventually what happened, what? And then it says, all right, I'm still looking for the height, and then still takes 3 seconds to hit the ground. Now I'm asking, what's the height of the cliff? You think about this. You say, all right, we're going to do the same approach, right? First of all, define a direction. I'm going to define going down as positive. Great. list the knowns. What do I know? I know that time is 3 seconds. That's great. I know my initial velocity. What is my initial velocity? You say 1 meters per second. Not 1 meters per second. What is my initial velocity? Negative 1 meter per second. Why? Because if I define going down as positive, going up is going to be what? Negative. Okay? I mean, it might be counterintuitive. That's fine. You can just what? Flip it around and define going up as positive. Then your gravity will be what? Negative, right? So you plug in. Then if this is positive, that means you define going up as positive, then this will be what? This will be negative. So be very flexible, right? Understand, no matter what you do, it has to make sense. The sign has to make sense. Keep good track of signs, right? If you define which one is positive, you don't have to worry about it, right? A lot of students get confused with like, I don't know whether it's positive or negative. Have a very clear way of labeling, have the signs ready, and you'll get there. Okay? Now, when that's done, you say, wait a minute, Lynn, this is not the height, right? Because how is this box going to travel? Well, the box is going to travel like this. We all agree it's going to go up and come down, right? Height is what I'm looking for here, right? But the actual trajectory of the box goes up, then comes down, right? And you say, but that's not displacement, is it? What do we define as displacement? Displacement is the difference between where you start and where you end up. You start here, you end up here. Your displacement in this case is your height. What are you thinking about? You're thinking about the distance. This is the distance this box traveled. It went up, came down like with a loop, plus the height that it dropped. Do we care about that? No, because we care about the displacement, which is the height here, so we don't have to worry about the path it went through. We're not dealing with distance. Hence, we can simply use what? Use this equation again. Okay? We can use this equation again. So that's the beauty, again, that's the beauty of using displacement, because I don't care how the path of the box goes. I only care about where it starts, where it ends. That's my displacement. Okay, that's done. So let's quickly pop it in. Displacement initial velocity times time plus 1/2 a t squared. -1 times 3 plus 1/2 times 10 times 3 squared. -3. This is 9, right? 9 times 5 plus 45, 42 meters. Remember the previous problem, it's 40, to what, 45? The difference is what? Well, the difference is it still took 3 seconds for the thing to fall. It has to be a shorter cliff, right? Because the box has to travel up then come down, right? It takes the same amount of time, so the cliff has to be short. That has to make sense, right? Physics has to make sense. And I want you guys to think about this again. The argument I made about the difference between displacement and why we use it, and why it's displacement here instead of distance. Because if it's distance, we got to calculate how long it takes to go up, how long it takes to go down. It doesn't matter, right? Displacement simply says, this is what I care about. Okay? So it makes your life easier. Don't get confused. Okay? So that is the gist of free fall. With that in your mind, I'm going to kind of deal into one of the most commonly tested problem in kinematics, and hence the topic of today, projectile motion. What is projectile motion? We've all seen it, right? Projectile motion is launching something. If I want to toss something between this point and this point, would I toss it straight? No, why? That's stupid. Why is that stupid? Because if I toss it straight, what would happen? If I'm here and I want to land it somewhere here, right? I wouldn't toss it straight, because if I toss it straight, it's going to drop, right? Why? Because there's gravity. Gravity works on this object constantly. Okay? So gravity drags it down. So in order to do that, in order to compensate for the fact gravity is dragging it down, what would I do? I would toss it up. Because when I do that, even though gravity still drags it down, I can compensate for it. Right? I can compensate for it. And that is the gist of projectile motion. So you can see projectile motion is simply what? A two-dimensional motion. Right? Two-dimensional motion. You launch it with an angle. Every projectile motion starts with two things. One, what is your initial velocity? And what is the angle that you're launching the projectile? Okay? So you have a VI and you have a theta. Okay? And the three things they always ask you when it comes to projectile motion is, one, how long would it take for it to land? Two, how far would it go? And three, how high would it reach? If you can answer these three things, you're done with any projectile motion. And I'm going to show you how easy it is to do. Okay? We know if we launch something like this, this is what the projectile is going to look like. Right? Assuming it lands in somewhere level, but it doesn't really matter. Okay? Here's what you do. First, whenever you see projectile motion, it's a two-dimensional problem. We can't deal with two-dimensional problems. Okay? What we're going to do is separate. Okay, remember how we did vector decomposition? We're going to decompose this vector into two separate ones. If you don't do that, you cannot solve any projectile motion. I'm going to decompose this VI into two of its components. VI in the x direction and VI in the y direction. I'm not going to solve a simple two-dimensional problem. I'm going to break it down to two one-dimensional problems and tackle each one individually. Okay? You know VIX, which is simply what? It uses a little trick. It's VI times cosine theta, and VIY is VI times sine theta, right? If you do any projectile motion without breaking down your vector components, you're not doing right. You're getting it wrong. If you just use the VI that they provide, you're not doing the right question. Okay? You cannot get the right answer. So whenever you see a projectile motion, break it down instantaneously, because that's what you need. Break it down to VIX and VIY. Okay? The initial velocity in the x component, the initial velocity in the y component. And this is the beauty of it. What is it? It's that these two motions are motions that we're familiar with. Okay? The x component motion is a constant velocity motion. It's a constant velocity motion, which means there's only one equation that governs the entire motion. Because without gravity, you toss something, if you go out of space, you toss something straight, guess what? How this truck is going to travel? It's just going to go, no acceleration, nothing. It's just a constant velocity motion, right? It sounded weird, but that's what it is. So this VIX is just really Vx, because there's no such thing as a V final x, because all of them are the same. And all you have to do is that this Vix, basically displacement in the x direction, is Vx times the time it takes for it to fall. That's it. There's only one equation because it's constant velocity. I just rearranged it, and that's it. And what's delta s of x? This is delta s of x. Okay? Another fancy name for this guy is the range of the motion. Okay? How far it went. Right? But we can't get that because it's a constant velocity motion. We don't have a sense of how long it takes, because without the other motion, it will go on forever. Right? So time, the first question you need to ask yourself, how long does it take, is not controlled by the x. It's controlled by what? By the y component. Why? Because the y component, as you guessed right, is a constant acceleration motion. Okay? It's in a constant acceleration motion with what? It's not even a, it's a constant g motion, right? It's a free fall problem. That's all it is. It's a free fall problem. Why? Because it's like that box example I gave you. What happened if you just look at the vertical component of your trajectory? What does it look like? It goes up and it comes down, right? It hits the peak, it slows down because gravity drags down, right? It slows down until it reaches 0 and comes back down again, right? And that's the y component. And the x component just goes straight. Because if you combine the two, it looks like comes up, comes down. That's what causes the projectile motion. So there are two components acting on the same time. So if it's constant acceleration, it's a free fall problem, all we need to do is what? Use these three equations, right? And they're applicable. They're applicable. For instance, I'm going to find out the time. How do I find out the time? How do I find out how long it takes to go up and come down? Well, I'm going to find out time through this equation, right? So everything will be in y because displacement in the y direction will be VI y times t plus 1/2 gt squared, right? I just rewrite this equation simply, right? Think about it. What is your displacement in the y direction? That's a very important point. If your projectile motion, this is the level of ground, goes up and comes down, what is your displacement in the y direction? Displacement, not distance. Again, keep on emphasizing that. Your displacement is 0 because you come up, you come down, right? The net displacement in this case is 0. Look how easy this problem becomes. You have 0, right? And you know what VIY is because you calculate here. It's just VI times sine theta times t plus 1/2 of 10 times t squared. This is a number. This is 0. T, right? You can actually factor out a t and solve for it. You're done. Okay? Look how simple that problem is. You can simply get t like that. Right? Once you get the t, you can simply plug this t, right, in here. That's how they're connected. You can simply plug the t in here, right? And you know the Vx, and you can get your delta x. So you get how far it went. Done. Right? You say, Lynn, what about problems that, you know, let's say it clears a hurdle, right? It comes up, it just want to know, let's say there's a goalpost, like certain distance high, right? It goes up, you're not going to hit the ground level, but you're going to hit like a little bit above ground. What I do? Well, in that case, your delta sy is not 0. It's whatever how high the goalpost is. That's 10 meters. The only difference is that this becomes a quadratic when you solve for t. Big deal. You guys in AP Physics, you can solve a quadratic equation, right? Not that difficult. But what I'm trying to tell you guys is nothing is changing. Nothing's out of ordinary for these three, right? For constant acceleration. It's always the same equations. I want you guys to be consistent, okay? And then, if you take a look at this and say, well, what about how high? Well, we know when we reach the highest point, it's a y direction motion. We can simply use what? V final square plus V initial is equal to V initial plus 2a delta s. How? This is the height I'm looking for, right, in terms of y. All this is in the direction of y. I know this guy. I know this guy. What's your final velocity in y when it reaches the highest point? If you think about it, you toss something out when it gets to the highest point, the y component is what? 0. Right? And you know this, you know that, you can solve for height, and you're done. That's it. Very simple, right? So, you get how long, you get how far, and you get how high. Okay? Let's take a look at an example, and then really demonstrate how this is done. I'm going to show you a very, very simple number. So I can actually work on a board without a calculator. You're launching something at 10 meters per second with a 30-degree angle. 3 questions. How far? Well, how long? displacement in the x, displacement in the y. Okay? How long, how far, and how high? All right, 3 questions. What I do, decompose this. Vx is going to be 10 times cosine of 30, right? What's cosine of 30? Square root of 3 over 2, I imagine, right? 5, and square root of 3 is like 1.7, so 8.5-ish. I mean, this is just rough numbers, right? Always get these components first. Done. Vx is done. Vy is equal to v times sine theta, which is 10 times sine of 30, which is 1/2, so 5. V initial y is equal to 5 meters per second. I always get these 2 first, okay? I'm always interested in timing, right? Time. What is the time? So if I look at this, right? It's a y. Always label, if it helps, whether it's an x component or y component motion. If it's a y component motion, just put a y next to it so you know you only deal with y. You're going to use what? Displacement is equal to initial velocity times time plus 1/2 at squared, right? You can define going up as positive, going this way is positive, so x is always positive, and going up is positive. That's great. What's your displacement? What is y displacement for this whole motion? It came up and went down, so from a y perspective, it's 0, right? So 0 is equal to universal velocity is 5 times t plus 1/2 of, well, what's your a? -10 times t squared, right? Why is it -10? Because gravity is always going down, right? You define going up as positive, so it's -10. Great. So you get 0 is equal to 5t minus 5t squared if you factor out a t, and t turns out to be 1 second. Done. Timing for this to take place is 1 second. I made up the number really simple, so there you go. Okay? That's great. You got the timing. What's next? Well, what's next is how far it went. Delta x, delta s in the x, right? I know just Vx times t, which will be 8.5 times 1, which will be 8.5 meters. Done and done, right? Both of them done. And last one, what's the height it reaches? I know that's going to be v final squared is equal to v initial squared plus 2a delta s. Again, everything's in y, and this is 0. V initial is, here is 5 squared plus 2 times -10 times delta s. Right? Delta s, in this case, in the y direction, is your height. So 5 squared, 25 minus 20 delta s. Delta s, this is 0. And delta s in the y direction is 25 over 4, 1.25 meters. That's it. See how simple that is. You never have to get all 3, right? But I'm showing you just by using this, you can actually derive the entire board. Okay? The entire board. I'm going to leave you guys with this. I want you guys to practice with your textbook, practice with problems with projectile. Just keep in mind, always use the same approach. Decompose, do the x, do the y, find out timing, and do everything else. Keep it consistent and don't complicate the problem. That's all you need, okay? Don't memorize any other equations. You don't need any of that stuff. Okay? Always be able to go back to the fundamentals, and this is the fundamental. Okay? One thing I want to leave you guys with, what if I change this? What if I change this to launch this at 10 meters per second? So same velocity, but 60 degrees. I want you guys to repeat the same calculation, but with a 60-degree angle. Okay? you will find something really interesting. I'll let you guys do it. You can pause and then come back right now, and you'll see that you're going to get the same displacement in the x direction. So the range of motion will just look like this, but it will still be 8.5 meters. Is that a coincidence? It's not. It turns out that when you are filing projectiles with complementary angles, you're always going to get the same range. One is going to get there faster, one is going to get there a little bit slower. But one looks like this, the 30 will look like that. Okay? So something to calculate, to figure out.